Okay, so good evening, everyone. So I am Keshav. I am research scholar at IIT Kanpur. So I am taking this problem solving session for week 11 of NPTEL course ME111. Okay, which is applied numerical method. So there is one more student joined here. So please introduce yourself in the chat box. Hello, am I audible? Okay. So please introduce yourself in the chat box if you can. So let us start now. So till now, what we have covered in this course, we have covered numerical method for linear algebra. There we have seen two types of problem. One was what? Ax equal to b type of problem. And second one was Ax equal to lambda x type of problem. This is system of linear equation. And this is eigenvalue problem. So we have seen the numerical method that can be used to solve system of linear equation and to find the eigenvalues and eigenvector of a square matrix. Then we have covered the numerical method related to calculus. There we have seen first numerical differentiation. After that, we have seen numerical integration. In numerical integration, first we have seen interpolation. Interpolation, we have the data at the discrete points. So we fit the interpolating polynomial, and while integrating that interpolating polynomial, we can find out the numerical integration. Then we have seen how we can do how we can solve the ordinary differential equation and partial differential equation using numerical method. Okay. In the last week, we have seen regression. Okay. So this is what that has been covered till week 10 in this course. Now in week 11, we will see optimization problem. Before I go to week 11, let me show the plot of last week. Since I think I have shared only the MATLAB window. So you guys were not able to see the plot that has been come after the regression. So it will take only 2 minutes. Okay. Okay. This was the question we had that has been there has been given some x and corresponding y. We need to fit a regression for this w0 plus w1x plus w2x square. So if I run this, so w0 is 0.5343, w is minus 0.2986, and w2 is 0.244071. And this is the figure. This is the figure. So red dot is representing the training data, and the blue one line is the regression table. Okay, so this figure was not popping out in last week because I think I have said only the MATLAB window. Okay, so this is what I wanted to show from last week. Okay, so what we do in optimization, we wish to minimize the function f of x. It can be a multi-variable function, or it can be a single variable function. But here we are considering now single variable function. So we wish to minimize some function f, which is called objective function, which subject to some constraint. This constraint can be inequality type, or it can be of equality type. If it is inequality type, it is called inequality constraints. If it is equality type, it means the constraints are equation, then it will call equality constraints. Okay. So here, how many inequalities are there? M number of inequalities are there, and P number of equations are there. M and P are equal to 0 means there is no inequality and there is no equation constraint for the given minimization problem. So that problem is called as unconstrained optimization. Okay, that problem is called unconstrained optimization problem. You would have studied the linear programming in your 10 plus 2 course. So the optimization problem is called as linear programming when the objective function and the constraint both are linear. Then it is called as linear programming. Okay. Similarly, quadratic programming, when the objective function is quadratic and constraints are linear. Function is quadratic and constraints are linear, then the optimization problem is called as quadratic programming. Okay. All other type of optimization problem is called as non-linear programming. Yes. Now, suppose we want to do the maximization. We want to solve a function to find its maximum value. Okay. So the maximization problem can be converted to minimization problem if we consider some phi that is equal to minus of f of x. So if we want to maximize f of x, which means we need to minimize phi of s, where phi of x is equal to f of x. So suppose if there is some function this f of x like that, okay. So it's having some maximum here. So if I plot the minus of f of x, that will have the minimum at the same location, but with minus sign. Okay. In this way, we can convert a maximization problem into a minimization problem. Okay. Very easy. Similarly, if you remember, there can be if there is a function, there can be many local maxima and local minima. So wherever there is a maxima, the condition for maxima is what? Condition for maxima is what? F of x is equal to 0 and f double prime of x should be greater than 0, if I am right. Right? Okay, less than 0. If f of prime is less than 0, then there will be a local maximum. Okay. Similarly, if f of prime is equal to 0 and f double prime is greater than 0, then it will be a local minimum. So the global maxima is defined as the maximum of the all the local maxima. Similarly, global minima is defined as a minimum of all the local minima. So here what we will study the convex function where local minima is global minima only. Okay, the function will have only one minima, and that will be the local that you can call local minima or global minima. Such type of function are many a time encountered in the engineering problem. So we will study only that type of function in this course. Okay. Now we will start with the simplest case, which is 1D unconstrained optimization problem. Here in this course, we will study only unconstrained optimization problem. Okay. So first we will start one-dimensional unconstrained optimization problem, which is also called as single variable unconstrained optimization problem. Okay. So in general, what will be the case? In general, we wish to minimize y that is equal to f of x, and this x is a vector. This x is equal to variable x1, x2, xn, means it has n dimensional vector. Okay. So we want to minimize this f of x. Means what? Mathematically, we want to minimize the function. This x is belongs to n dimensional real space, and this function is what? This function is defined from Rn to R. Okay. So what? Real vector R and y is a real scalar. Okay. Global maximum is what? Sorry, global minimum. Are you able to hear me? Okay. So global minimum is what? Means we want to find the minimum value of x. We want to find out the minimum value of f of x for all x. Okay. For all x. But local minimum means what? We want to find out the minimum value of f of x in the neighborhood of x1 only. Okay. So some neighborhood defined, on that neighborhood only we want to find out minimum value of f of x. So if we write in 1D case, so x will be scalar, x will be some one value only. So x will be scalar, so y will be also a scalar. So this function is what? Defined from real space to real space. Okay, 1D real space. Now let us consider an example to understand 1D unconstrained optimization problem. So suppose we have some experimental data. We have some experimental data for fuel economy, kilometer per liter at different speed. This is the experimental data that we have. We have done the experiment at different speed of the vehicle, and we have found out what is the fuel economy. Okay, then what we do, using this experimental data, we fit a regression. Okay, we fit a regression to find out a regression curve. Suppose we have found out this. Okay, and now we want to minimize the fuel economy, since we want to pay minimum amount of price. Sorry, fuel economy means kilometer per liter, means what? We want to go as many as kilometer per liter as possible. So we wish to maximize this function f of x. So for maximization, we need to do f prime of x equal to 0. That will give me a stationary point. Then at the same point x star, I will find f double prime x. If this f double prime x is less than 0, then that will lead to maxima. And if this f double prime x at x equal to x star gives me is greater than 0, that will lead to minima. Okay, so let us differentiate this. So that will be equal to what? This differentiation of this 3ax square, differentiation of this 2bx plus p. That is what we have written. Now we will impose the condition f prime x equal to 0. That will lead to x equal to minus b plus minus b square minus 3ac divided by 3a. Now you put the value of a, b, c, d here, then you will get two values of x. Okay, this is the two values of x. Now you find out the f double prime at both the point. If the value comes positive, means what? It is minima. If the value comes negative, means what? It is maxima. So at x equal to 65.625, the value is negative. So here we will have a maxima. So the value of maxima will be what? Y max means what? The maximum fuel economy. That will be f x at f x at equal to 65.625. That will be equal to 18.58 kilometer per liter. Okay. But the main issue here is many a times the analytical solution of f prime x equal to 0 is not available. Okay. If this is not available, so what we can do, we can use the root finding techniques that we have studied in week 1 to find out the root of f prime x numerically. Okay. Means what? The problem, optimization problem in one dimensional unconstrained case is converted into a numerical problem of root finding method. And we already have studied the root finding methods. Some root finding method we have studied, some we will discuss here. Okay, so let us move towards the numerical methods to solve this one dimensional unconstrained optimization problem. So the simplest method can be a random search method. Random search method is what? A trial based method, and this comes under the family of meta heuristic method, which is based on trial or common sense method. Okay, in which what we will do, suppose we want to find out the minima of f of x in some interval from x1 to x2. Okay, in this interval we want to find out the minimum value. Fine. So what we'll do, we will randomly take some x that belongs to x1 and x2. Okay, we will take this x1 and x2, some randomly x between x1 and x2. Then we will find f of x corresponding to this value. And then again I will do that. And if the f of x that I have found is less than f of x, suppose this is my at kth iteration, at some k minus 1th iteration, if it is less than this, I will replace this x into my desired x. Okay, like that I can find out the minimum value. Okay, how we can do, let me add one more page here. Okay. So suppose I have assumed some x randomly between x1 and x2. Okay, I have some x store variable here that is initially equal to 0. Okay, now what I will do, or I can assume x1 or x2, x1 or x2, x1 or x2. Now what I will do, I will put this to find f of x. Okay, so suppose here I have assumed earlier f of x, so I will find f of x1. this x that I have assumed randomly. Now I will check. Now I will check f of x. If this condition is satisfied, then I will replace x store equal to the x that I have randomly selected. Again, I will choose x randomly from x1 and x2. Then I will find check what check. I will check f of x. If this is less than f of x store, then what I will do? I will I will replace x store to x. Okay, like that. So this is the random search method to solve 1D optimization problem, unconstrained 1D optimization problem. Now we will see root finding by optimization. So earlier what we have seen? We have seen that the optimization problem can be converted to a root finding method, root finding problem. Okay. So the reverse is also true. Means what? A root finding problem can be converted to a optimization problem. How? So suppose we want to find the root x star of f of x. Then we can do or we can solve minimization problem of phi of x, where phi of x equal to f of x whole square or phi of x equal to modulus of f of x. If you plot, if you plot, suppose I am plotting f of x, so this f of x can be positive or negative. Okay, this can be positive or negative. If I take the square, so all negative terms will be also positive. Only the zero term will remain here. So if I plot, so this will be equal to, suppose I am taking modulus, so this will be converted like that. So the minimum point will be the roots only. Okay. So suppose if I want to find out the value of root 2, what I can do? This I can do by finding the root of f of x equal to 0, where f of x equal to x square minus 2, or I can solve for minimization of phi of x, where phi of x equal to x square minus 2 whole square. Okay, sure, sure. We'll join after 5 minutes. No problem. Clear? So what we have discussed in now? So first we have seen how we can find the, how we can optimize the problem, how we can solve the optimization problem using analytical method. Then we have seen that many a time this analytical solution is not possible. Then we need to go for numerical methods. There we have seen first random search method. Okay, random search method for 1D unconstrained optimization problem. Now we will see reason elimination method. Okay, this method is very useful for optimization problem of a continuous function. Okay, in a specific interval. So suppose we have a function y equal to f of x, which is having only one maxima or only one minima in x1 and x2 interval. Okay, so now we are considering the maxima case. So what we'll do, we will decrease this interval x1 and x2. Okay, so suppose I have this function f of x here. This f of x is plotted here like that. Okay, this is f of x. So I need to find out the maxima between these 2 points. Okay, Okay. Now what I will do, I will take 2 points x1, sorry, x3 and x4 such that it lies between this. Means what? This x3 is greater than x1 is less than x4 and this x4 is less than x2. Means what? The x3 lies somewhere here and x4 lies somewhere here. Okay. Now we will check what? We will check f of x3. Okay. We will check f of x3 and f of x4. If this f of x3 is less than f of x4, what we will do? We will replace our interval x1, x2 to x3, x4, x3, x2. So means we are solving for a maximization problem. So at which point the value is coming minimum, that point will replace my interval. Okay. So here x3 is giving the function value lower compared to x4. So x we will replace x1 to x3. Similarly, if x3 is greater than x4, so this x4 will replace x2 here. Okay. How it is happening? Suppose I have found out the value at x3 and x4. Okay. So it is coming that f of x3 is less than f of x4. Means what? Is somewhere lower than. Okay. Now the function is greater than here. So it is moving like that. Okay. It is moving like that. So so if the function is coming like that, for continuous function, it will go like that only. Na? It cannot go like that. If it will go like that, then it will be wait a second. Just 1 second. Now we know what the function is having one maxima. Okay. Here function is having one maxima. So if this value is greater than this value, so my function is going like that. Okay. So it will become like that. So here this value is less than this value. That's why we are neglecting. That's why we are neglecting x1. Okay. And we are considering this x3. Okay. If this is other way around, means what? The value is somewhere here and this value is somewhere here. So my function is going like that. In that case, the function will go like that. That's why we need to neglect this part. That's why we have considered this x1 to x3, x4, x1 to x4. Okay. Now, if we have minimization problem rather than maximization, we will check the same condition. But if this is the case, the f of x3, if the f of x3 is less than, then we will replace x2 with x4. And if the other way around, we will replace x1 with x3. Here. So this is a which method? Region elimination method. Okay. So we should choose x3 and x4 such that we reach the converse solution in less number of iteration. Converse solution means what? We have some interval initially, then we have decreased the interval. So converse solution means what? We want to decrease the interval to very small value as soon as possible in minimum number of iteration. So we need to choose the x1 and x3 and x4 such that we come up to the converse solution, means was very small interval in less number of iteration. So there can be many possible ways to choose x3 and x4. So one of such method is golden section search method. Okay. In this method, what we do, we will define new interval that will be equal to constant multiplied by previous interval. Means what? If I am having some initial interval x2 minus x1, which is having length L, then my there is one mistake here. Okay. So my new interval length will be what? Some constant multiplied by L. Okay. Then there is second condition here for here, which is the same rule applied for finding x3 and x4. Okay. So the condition is like that. This length is what? My L. Okay. So this x1 to x4 is CL. This x2 to x3 is CL. Okay. The condition is like that. The x4 minus x1, x4 minus x1 is what? From here to here divided by total from here to here. That will be equal to x4 minus x2, means what? This is smaller one. This is smaller one interval. This is smaller one interval divided by x3 minus x2, means what? This interval. Okay. So what we are taking here, we are considering here the ratio of this and total, the ratio of this and this will be equal to the ratio of this and this. Okay. So this can be written, if you add and subtract x1, you will get c will be equal to 1 minus c divided by c. That will lead to a quadratic equation, c square plus c minus 1, means what? C will be equal to minus 1 plus minus root 5 by 2. Since c cannot be equal to cannot be less than 0, c is greater than 0, means what? Minus 1 plus root 5 by 2 is the only possible root, which lead to c that will be equal to 0.618. Means what? Every time I am decreasing my interval to 60% or 61% or 61.8% of earlier interval. Okay. So this is the what? This is golden search, so golden section search method. Okay. This is a type of region elimination method. Okay. Now other method is Newton-Raphson method. In Newton-Raphson method, what we will do, suppose we want to find out the minimum of this function f of x. So we take some initial guess x naught. At this initial guess, what we will do, we draw the tangent, and wherever the tangent hits the x-axis, we consider this point as a root of this function. Okay. So means what? By x1 at the first iteration, I assume that at x1 I will get f of x equal to 0, and by doing this procedure I find out x1. Okay. This is we have discussed in. Okay, you are asking calculator are allowed in the exam? Question mark. So I need to confirm that. In the exam, can we do analytical method or we use any computer programming language for solving the problem? No, in the exam, you will not allowed to write computer program, because there won't be any question for the computer program. You need to solve the problem using pen and paper, using this numerical method. Means suppose you want to find you suppose there is a problem to solve using this Newton-Raphson method. So what you need to do, you need to assume some x naught, then you need to find x1 using pen and paper, using hand calculation. Okay, and calculator, that I need to confirm. I don't know whether the calculator will be allowed or not, but this is I am sure that they will not ask any computer program in the exam. So you need to do only pen and paper based calculation in the exam. So this is what the Newton-Raphson method that we have studied. Now here what is our goal? Our goal is to minimize this f of x. So we make some initial guess x naught, and we update our guess to x1. This x1 will be equal to x naught plus h naught d naught. So this h naught is known as step size, and d naught is what? Descent. Okay. Descent show the direction of our movement. If our f prime of x, if our f prime of x is greater than 0, like this case, then we will move in the left direction. Means what? Our x naught or f x of 1 will be less than x naught. Similarly, if my f prime at x equal to x naught is less than 0, in that case we need to move rightward. Means what? Our x1 will be greater than x naught. Means what? The gradient, this descent, I can assume as f prime of minus of f prime of x at equal to x naught. Okay. So then by using the Taylor series, I can find that this x at the first iteration, that will be equal to x at the 0th iteration minus f prime x at 0th iteration divided by f double prime at 0th iteration. If you remember, once we are finding the root of this f of x, then the formula leads what we got the form in the formula, x naught minus f of x naught divided by f prime of x at the 0th iteration. This is what we have found. Now in optimization, what we are doing, we are finding the root of f prime x. So you simply replace f with f prime. So this f prime will become f double prime, and this f will become f prime. So this is what the formula. Okay. So for any k plus 1th iteration, I can write that will equal to x at kth iteration, f prime at kth iteration divided by f double prime kth iteration in the minus sign. Okay. So we are finding the slope, and accordingly we are moving towards the solution. Okay. So this methodology, when we are finding the slope and moving towards that, is a general procedure of what? Gradient based optimization problem. Okay. So this is gradient based optimization problem, and this is a default method for many numerical optimization problem, optimization solver that are available. Okay, so this is kind of default and standard method, this gradient based method. Okay. Now, if we move towards multi-dimensional unconstrained optimization problem, in that case, this x is not a scalar, it is a vector. This x is a vector, and it belongs to some n-dimensional real space, and this f is defined from Rn to R. Okay, so x is defined like that. Now, what will be the necessary condition here for the maxima or minima? Necessary condition will be what? At this point, my gradient should be equal to 0. And what will be the sufficient condition? Sufficient condition will be what? This gradient should be equal to 0, and Hessian should have a positive definite value. Okay. So how the gradient is defined? Suppose if my x is defined like that and my function is this, then my gradient will be what? Del f upon del x naught, del f upon del x2, del dot dot del f upon del xn transpose. Okay. Similarly, the Hessian is defined as, first you take this f double derivative with x1, then you take del 2 f upon del x1 del x2, then del 2 f upon del x1 del x3 in the first row nth column, del 2 f upon del x1 del xn. Similarly, for row 2 also you can write, then row 3 and row n also you can write. So let me insert a page here. So my gradient is what? Gradient is what? Del upon del f upon del x1, del f upon del x2, del f upon del x3, del f upon del x n. Okay. If I want to find the Hessian will be equal to its transpose. Okay. Hessian will be what? Del f upon del x1. Then first row means what? First I will do the derivative with respect to s. Then second row, second column, derivative with respect to x2. First row means del x1. Third column del x3. First row del x1. Nth row del xn. Similarly, second row, so del x2. First column del x1 1. Second row, second column del x1 del x2 del x2, that will be equal to del x2 square. No? Similarly, nth row del 2f upon del xn del x1 since first column, del 2f upon del xn since the nth row, and second column is x2 f nth row nth column. Okay, like that. Now what do we mean by this Hessian is positive definite? Means what? It's all the eigenvalue should be positive. Okay, all the eigenvalues should be positive, and if I take any y in Rn, then this expression should give me a positive value. Y transpose Hessian y should greater than 0, and this can be found out that Hessian is having a positive value if I find out its determinant and it comes greater than 0, and this first element of the matrix is greater than 0. This is Sylvester criteria. Okay, this is Sylvester criteria. So I need to check what? I need to check the determinant and first element. Okay, so this first element is del 2f upon del x1 square and determinant of it. Okay, these two I need to check. If these two conditions can be satisfied, then I can solve the multi-valued unconstrained optimization problem using analytical method. Okay. Sorry, this is not any. This is analytical only. Now we have came to a term this gradient. Now, so let us discuss about this gradient. So suppose I have some function f of xy that is equal to x square plus 2y square minus 2xy minus 2 equal to 7. Okay. If you plot this, it will come like that. This is the elliptic equation, so it will come like that. Okay. Okay. Now I find out derivative at minus 1 comma 1. So this is my point, minus 1 comma 1. This is my point. No? So I find out the derivative here. So derivative comes as 1. Means what? The slope of the tangent the slope of the tangent will be what? At this point, the slope of the tangent, this is the dotted line is tangent, is 45-degree angle. Okay. So normal will have how much angle? Normal will have 135-degree. Okay. Now we find out the gradient. So the gradient will be what? The gradient will be del f upon del x1, del f upon del x2 transpose. If you find the gradient 2x minus 2y minus 2, 4y minus 2x. From here 2x, this will be 0. When x respect to x, we will do the derivative. This will be equal to what? Minus 2y minus 2. That's why it is written like that. And this will be 4y square. 4y square is here. Sorry, 4y. And from here 2x. So if you find the gradient at the given point minus 1 comma 1, it will be equal to 6 minus 1 1. Means what? Means what? This gradient is a vector which is 6 minus 1 1. Which means what? This gradient is pointing towards that. Okay, this gradient is pointing towards that. Means what? The gradient indicates the direction of normal. From here we can say the gradient is indicates the direction of normal. Okay. Now if we take three of this kind of function and we find out the gradient, all of the gradient will come same. Means what? The normal for all these are same. Okay. So if you plot it like here, it will come something like that. Suppose this is my first one, this is my second one, and this is my third one. Okay. So suppose at some point, this point, I need to find out the gradient. So all gradient will come like that. Means what? Which is normal to the function. If it is normal to the function, mean what? If I want to move from f to g or f to p, the gradient direction will give me the shortest path, since the normal is the shortest path. Okay. Now from here we can say that the function f increases at fastest rate if we go in gradient direction. Okay. And it will decrease with the fastest rate if we go in minus gradient direction. Okay. Clear? Now if we consider this function x square plus 2y square minus 2xy minus 2x, so at different xy value it will give me a 3D surface. And if I find out this at some constant c, so this will give me a family of 2D curves for different values of c. So this 2D curves we call as contour. Okay. So suppose if I want to minimize this function, so we focus on the contour and move. We want to minimize it. So minimize it. It decreases fastest rate in minus gradient direction. So now what we'll do, we will find its gradient and we move opposite to gradient to find out the minima. This method is called as gradient descent method. Okay. And it is very important method. Most of the practical problems now that are data driven, that are optimized using the gradient descent method only. Okay. Now, so what we do in gradient descent method, we want to minimize f of x. We assume some initial guess x0, x at 0th iteration, and we update our x at k plus 1th iteration. That will be equal to x kth iteration plus some step size and some descent. Okay, such that my f at the k plus 1th iteration should be less than f at kth iteration. Okay, so this dk is what? Descent direction, and this hk is what? Step size. Okay, if you applied the Taylor series, you will get this f at k plus 1th iteration, that will be equal to f at kth iteration plus hk plus dk transpose gradient of f at k and some order, higher order term. If we neglect the higher order term, this is what the change in f when we move from kth iteration to k plus 1th iteration. Okay, so this is the change, delta f equal to hk dk transpose gradient of f at k. Okay, so if we want to minimize this, this comes under the positive summation term. So this delta f should be less than 0. Means what? This term dk transpose gradient of f at xk should be less than 0. Okay. This term is what? This is what? This is directional derivative in the direction dk. Okay. This is the fundamental theory of gradient descent method. Okay. This is the fundamental theory for the gradient descent. Depending on dk and hk, there are different method can be possible. Okay. So suppose we want to solve this problem, this three problem. If I find out the gradient, this will be equal to this. Now I want find out the gradient value at -1, 1. This is equal to this. Now suppose this is my kth value. So at some kth iteration, I have the value -1, 1. Okay, this is my kth iteration value. Now I found out this function value at this point, and this is my gradient. Now what I will do, I want to satisfy this dk. I choose dk such that it should be less than 0. Okay, so I am assuming dk equal to d1 d2 transpose. Now you put here, you do the multiplication, you will get 6 d2 minus d1, which should be less than 0 according to the gradient descent theory. Means what? As long as I am taking d1 that is greater than d2, my this condition will be satisfied, and this will lead to f at k plus 1th iteration will be less than at kth iteration. Therefore, all directions such that d2 is less than 0 are valid descent direction. Okay. Now, what we have seen, this is the fundamental condition for fundamental theory for gradient descent method, and there are different choices. If I take different choices of dk and sk, I will lead to different method. Now we'll discuss different descent methods. So first one will be the steepest descent method. Okay, steepest descent method means what? I want to do this equal to 0. If I write, this is what? Nothing but the inner product. So inner product will be what? Magnitude multiplied by magnitude multiplied by the cos of theta. Cos theta, where theta is the angle between dk and gradient of this. This is a vector. This is a vector. So I am taking the dot product. So that will be equal to magnitude cos theta. Cos theta is the angle between them. So this will be minimum. So cos theta should be less than 0. Since it is greater than 0, this magnitude is greater than 0. So cos theta should be what? Less than 0. So the minimum value of cos theta will be what? At theta equal to pi, it will be -1. So if I take theta equal to pi, that will lead to steepest descent method. So the angle between dk and grad of f at xk is pi in the steepest descent method. Means what? At this point, suppose I have found out this is my direction of gradient. So I will take the direction, descent direction opposite to that. Okay. So I can assume dk will be equal to minus gradient of this. Okay. Now we know that this function will decrease at fastest rate in the direction opposite to the gradient. So this descent direction will lead minimization with highest rate in this direction. Okay. Now HK is what step size. So step size we can take constant, or we can obtain suitable HK using line search method. Means what? Means what I will do, I will find out this f at k plus 1th iteration, that will be equal to f at kth iteration plus hk dk. I know the dk, I know the x of k. So this will lead to a function phi, which will be the function of only hk. So now I can use the 1D optimization technique to minimize this phi to find hk. Okay. And this method I will do till what? Till my dk is, the norm of dk is very small. Okay. So this is multivariable unconstrained optimization problem. Now this HK is can be, this method will lead to the best solution, but this method can be a computationally extensive. Okay. So in some case, backtracking line search method is used to find the step size, where Armizo condition should be satisfied. What is Armizo condition? Where we impose that this f at k plus 1th iteration should be less than f at kth iteration, but we do not impose the minimum condition. And this, how we do that? The Armizo condition suggests that this condition will be satisfied. This condition should be satisfied, okay, for some value of beta in between 0 to 1. So what we'll do, we'll assume some beta 0 to 1 small value. We will check whether the Armizo condition, which is this condition, is satisfied or not. I will assume the h initially 1. I will check whether this Armizo condition is satisfied or not. If not satisfied, I will replace h with tau of h. This tau belongs to 0 to 1. Okay. Generally, it is taken 0.5, means what? We decrease the h by half to its value. And we continue till the Armizo condition satisfied. Okay. So this is what method? Steepest descent method. Now similarly, Newton's method can be also defined for multivariable function, multi-dimensional function. So this is what? Nothing but multi-dimensional Newton's or Newton-Raphson method. Means what? Here what we are trying to do, we are trying to extend the Newton method from 1D to n dimension. Okay. So in this case, earlier what we have xk plus 1, that was equal to xk plus, no, not plus, minus f prime of x divided by f double prime of x. Okay. If you change it to multi-dimension, this will change to gradient of x at kth, and this will change to Hessian of f at kth. So this is 1 by, this is in the denominator. So when it will go to denominator, it will become inverse. So this is what we will get. Hessian of f at kth iteration inverse multiplied by inner product gradient of f at xk. Okay, this is the formula. Now here also we can improve the convergence by using the Armizo condition, or satisfying the Armizo criteria. When we do that, this method is known as Cauchy-Newton method. Here what we will do, we'll put this is same, we multiply it with some h. Okay, and for h this condition should be satisfied. If this is not satisfied, we'll use this method to replace the h and satisfy this condition. Okay, Clear? Now what we'll do, we'll solve some assignment problem. Okay, we'll solve the assignment problem. So what you do, I will write the problem and I will also try to solve. You also solve and write the answer in the chat box if possible. Okay. So the first problem is what? We have a real valued function f of x equal to x square minus 54, sorry, plus 54 divided by x. Okay. So it will attain a minima at x equal to x star. Okay. Then you need to tell the value of x star. So this x star will be what? Okay, this is what we need to do. So what will be the solution? So for minima, I need to find out f prime of x and enforce it to 0. And then I need to check f double prime of x. If this is greater than 0, then it will be what? Minima. So I need to find first what? F prime of x. F prime of x. So that will be equal to 2x plus minus 108 divided by x square. This will be my, now you enforce it to 0. So 2x will be equal to what? 108 divided by x square means what? X cube minus 54, that will be equal to 0. Okay. Here it will be what? Minus n, x to the power n minus 1. So this will be minus 1. So it will come 54. So here will be also 54. So from here it will come 27. So from here x will be what? Minus 3. Okay. Now you find f double prime. F double prime of x will be what? 2x minus 54 upon x square. So this will be equal to what? 2 minus, this will be plus 2 multiplied by 54 divided by x cube. Okay. 3. So x cube will be 27. If you put, this will lead to what? 2 to 4. 4 plus 2, 6. So f double prime equal to 6, which is a positive number. Means what? At x equal to 3, f will have a minima. Okay. If it is having minima here, means what? So if I found out the minimum value, now you put there, so it will be 9 plus 24 4 by 3 to 27, that will be equal to 36. Huh? 36. Clear? If I am doing any calculation mistake, please let me know. Okay. This value is correct. X square will be what? 9. And here, if we would put 3, it will be equal to 8. It will be equal to 3. So it will be equal to 18. So 18 plus 9 will be equal to what? 27. Okay. So now we move towards the second problem. Second problem is what? F of x comma y is given as y minus x minus 2x square minus 2xy minus y square. Okay. This is a real valued function. If u is defined as gradient of f at 0, 0. Okay. So I need to find out u transpose u equal to what? Okay, this is what we need to solve. Please solve this problem. So first I need to find out what? F is what here? F of xy is y minus x minus 2x square minus 2xy minus y square. Okay, this is what we have. Now gradient of f will be what? Del f upon del x, del f upon del y. So this will be what? You do the differentiation. Minus 1 minus 4x minus 2y. Here differentiation will be 1, 0, 0 minus 2y, 2x, sorry, 2x minus 2y. This will be my gradient. Now you find gradient value at what point? 0, 0. That will be equal to u. Not looking at u. So u. So this u will be equal to what? From here. Here is 0. This will become 0. This will become 0. This will become 0. Minus 1, 1. Okay. Now I need to find u transpose of u. This is my question. So minus 1, 1, minus 1, 1. That will equal to, this will be multiplied by this will be multiplied by this. That will equal to 1 plus 1, 2. Correct? Okay. So the next problem is in the same question, what we have y minus x minus 2x square minus 2xy minus y square. In the same question, same f of xy attains a maxima at x equal to h and y equal to k. Okay, x equal to h, y equal to k. It's a chain maxima. Then we need to find h plus 2k. Okay, this is what I need to find. So we have found out the gradient, na? Gradient f of that was what? Here we have found out the gradient, na? -1 minus 4 x minus 2y, and here what we have 1 minus 2x minus 2y minus 2x minus 2y. This is what we have. Okay, so for maxima and minima, what we need to do? First we need to do the gradient equal to 0. Then what? Then we need to impose, find out the Hessian and impose the step criteria, na? So let us find out the Hessian. Here Hessian will be what? Del 2f upon del x square, del 2f upon del x, del y, del 2f upon del x, del y, del 2f upon del x, sorry, del y square. Okay, this will be my Hessian. So this is nothing but my del 2f upon del x. This is my what? Del 2f upon del y. Na? So if I find out from here, derivative with respect to x, it will lead to -4. Derivative with respect to y, it will lead to -2. Derivative with respect to y, -2. Derivative with respect to y, that will be equal to -2. So this is what we got here. Okay, Hessian. Now I need to do what? I need to put gradient equal to 0. Means what? From here to from here, what I will get? I will get 2y plus 4x, that will equal to -1, and 2y plus 2x, that will be equal to 1. Okay, if I subtract these two from here, I will get 2x will be equal to -2. So x will be equal to -1. Okay, and if you put x equal to -1, so this will be equal to what? This will be equal to -1 to 3. So y will be equal to 1.5. Correct? X and y I have found out. Now I need to check Sylvester criteria. Na? So Sylvester criteria for what? This should be a positive definite. Like from Sylvester criteria, my determinant date of this Hessian of f should be what? Should be greater than 0 and del 2f upon del x square. Sorry, matlab x1 should be greater than 0. These two conditions should be satisfied. So first this is less than this condition is for what? Minima, na? This condition is for minima. For maxima, this condition should be satisfied. So it should be less than 4. So this is equal to -4, which is less than 4. Now I will find out the determinant. Now I will find out the determinant. The determinant will be what? Eight minus 4, that will be equal to 4. Okay. So this is my, so it will attain a maxima at this and this. So this is the condition for maxima. Okay. Now we move towards the next problem. If I want to find out the maximum value, so this maximum value will be what? F max will be what? -1, 1.5. Okay. So you put in the equation. What was the equation? Y minus. This is the problem. No? So you put here value and find out the minimum value. If you do that, the minimum value will be what? From here, the minimum value will be what? 1.25. The maximum value is 1.25. Okay. Or you can do what? In this problem, you need to do the maximization problem. No? So you go for minimization of, you directly go for minimization of what? G, that is equal to minus f of x comma y. Okay. If you do like that, if you go like that, then what will be the value? My gradient of G should be equal to 0, which means what? Gradient of f should be equal to 0. That will lead to the same x. X will equal to -1 and y will equal to minus not plus 1.5. This is what? Now for G you find del 2 of G. Okay. If you do that, the terms that are negative will become positive. So it will be equal to 4, 2, 2, 2. It will be equal to this. Okay. Now you find out the determinant. If you find out the determinant of this, it will equal to 4 only. And if you find out the del 2G upon del x square, it will be equal to 4. Both are greater than 0. So it means what? G is minima. So f will be maxima. Like that also you can assume. Okay. Now the next problem. Now the next question is what? We do the minimization of function x comma y that is equal to 2x square plus y square plus 2xy plus x minus y. This is the function. We do the minimization using Steepest descent method. Okay, this method we want to use, and our initial guess is what? Or here our initial guess is x equal to 0, y equal to 0. Okay. So at x equal to 0 and y equal to 0, what will be my descent direction? Okay, descent direction. Okay, so I need to tell the descent direction at x equal to 0 and y equal to 0. So what will be the answer? It will be a vector, na? Means it will be a column matrix. So please tell me what will be the descent direction. Please reply on the chat box. Okay, solve this problem and reply on the chat box. So if you remember, the descent direction dk is minus gradient of f at x k. No, this is my descent direction. So you find out the gradient and put the value to find this dk. So what will be my gradient if I write? Gradient will be what? 4x plus 2y plus 1. 2y plus 2x minus 1. Now you put x equal to 0, y equal to 0. So, if from here, if I write, good. So if I write dk will be equal to what? Minus of this. So in variable format, if I write, this will be minus 4x minus 2y minus 1 minus 2y minus 2x plus 1. So dk will be what? At 0, 0, at 0, comma 0, it will be equal to minus 1, 1. Huh? So my value is different from yours. So am I doing some mistake here? Let us go to the steepest descent method. So this is the steepest. So yeah, it is minus, no, minus of gradient. Minus of gradient. So you check your value. I think you are getting wrong value. But there will be a minus sign. Oh, okay. Okay. So we move towards the next problem now. The next problem is what? In the next problem, we have this same function. Okay. This same function we have. Now what I need to do? I need to find determinant of Hessian of f prime inverse. Okay, this is what we need to do in this question. If f equal to f of x, y equal to this, then we need to find out this. So to solve this problem, first we need to do what? We need to find Hessian. For that, we need to find the gradient. So gradient will be equal to what? Or we can directly find out. No? So del f upon del x will be what? 4x plus 2y plus, oh sorry, 4x 4x plus 2y plus 1. Del f upon del y will be what? This will be equal to what? 2y plus 2x minus 1. Now from here, if you find del 2f upon del x square, this will be equal to 4. Del 2f upon del y square will be what? 2. And del 2f upon del x del y, that will be equal to what? 2. So from here, if I write Hessian, that will be equal to what? Del 2f upon del x square del x del y del 2f upon del x del y del 2f upon del y square. From here, if I write, it will equal to 4, 2, 2, 2. Now I need to find out the inverse. That will be equal to what? 1 upon det of determinant of Hessian. You replace this and change the sign of opposite. Okay. So this will equal to 2, 4, minus 2, minus 2. Correct? Now I need to find out the determinant. So determinant will be what? 4. So this will be equal to 1 upon 4, 2 minus 2, minus 2, 4. Okay. Now what we need to do, we need to find its determinant. Okay. So determinant of Hessian of f inverse. Okay. So this will be equal to minus 4 will be common. Now 8 if I put this value inside, this will be divided by 4, divide by 4, divide by 4, divide by 4. ना? So multiply होएगा तो क्या होएगा? This will be equal to 1 by 2 multiplied by 1 minus 1 by 2 multiplied by 1 by 2, right? So it will equal to 1 by 2 minus 1 by 4. This will equal to 1 by 4, correct? So 1 by 4 will be my answer. Good. Now last problem. No, this is not the last problem. Last problem. So now we move toward the last problem. So the last problem is what? The same f we have. This is the same f we have. We wish to minimize it using Newton's method. Okay. We wish to minimize it using Newton method. Our initial guess is what? Initial guess is what? X0 is 0, Y0 is also 0. Okay. Now, what will the value of X1 and and y1. This is what we need to find out. Okay. So in Newton's method, what is the formula for xk? Xk, sorry, xk plus 1 was what? Xk minus Hessian of f at xk inverse multiplied by gradient of at xk, right? I think we have found out the inverse for this, no? This is the inverse. We have already found out. So del square f was what? 1 by 4, 1 by 4, 2 minus 2, 2 minus 2 minus 2, 4. This is, and gradient of f is what? 4, 2, 2, 2. No, no, no. ये है ना 4x 4x plus 2y minus 1. 4x plus 2y plus 1. Then it will be equal to 2y plus 2x minus 1. Correct? Correct. Now I need to find out both x 0, 0. So this will be this will remain same. This f at x 0, this will be equal to what? 1 minus 1. Okay. Now I need to find out the inner product of these two. So so 2 plus 2. Here it will be what? Minus 2 minus 4. This will equal to 1 by 4, 4 minus 6, right? So this will be equal to what? 1, 1.5. Correct? Now my x at first iteration will be x at 0th iteration minus this whole term. So this is what? This is 0, and this value all we have already found out. So x1 will be what? Minus of that will be minus 1, 1.5. This is what our x. Clear? So this is the problem that we wanted to discuss. Okay. Now we will do one. We will write one computer program. So this is the problem we have. Okay. consider f of xy that is equal to y minus x minus 2x square minus 2xy minus y square. We need to write a computer program that uses Newton method to minimize the above function. Okay, we need to solve it and show the descent path from initial guesses to the last. Okay, in the control flow. So now I need to stop share from here. Now let me share from my computer. You are able to see my screen, no? Okay, so first what we need to do? First we need to okay, so maybe I should show something before sharing the screen from here. Hmm. So just to show you, this is my what? This is my gradient. You do the derivative of it, minus 1 minus 4 x minus 2y. Okay, and in the second row it will be minus 1 minus 2x minus 2y. Similarly, if I find double derivative, sorry, Hessian, that will equal to minus 4 minus 2 minus 2 minus 2. Okay, so this is what we want to do. X at k plus 1th iteration, that will be equal to x at the kth iteration, x at the kth iteration minus some h multiplied by the inverse of Hessian. Here will be gradient multiplied by the gradient at the kth iteration. Okay, if we find this value, the inverse of the Hessian, that will be the determinant of the Hessian, and you change these two elements and you change the sign of the off diagonal element. Okay, you change the sign of off diagonal element. That will lead to what? That will lead to this expression. Okay, so minus 2 to 2 minus 4 and 1 by 4. And if we do the multiplication of these two terms now, so this will be equal to what? From here we can take 2 outside. This from every term we can take 2 outside, and if you do the multiplication and solve, this is what we will get. So this will be equal to this 1 by 2, 2 plus 2x, and here minus 3 plus 2y. So this I can write like that. This will be equal to 1 plus x, and this will be equal to 2y minus 3 divided by 2. Okay, so these two terms we need to remember before start writing the computer program. Okay, this and this. No, only this and this function. Okay, these two things. Just 1 second. Okay, so first before doing anything, let me just write clear all so that I can clear if anything is already defined. CLC close all. This is not necessary. Then we will define some what functions and variables. So first thing what I can do, I can define x equal to, suppose 0 is my initial guess. So this is my what? Initial guess for x. Okay. Y equal to what? Suppose 0. This is my initial guess for y. Clear? Now I need to define the function. So in MATLAB, how we can define the function? Suppose my objective function is equal to, this is a function of x and x comma y. Now I need to write the function value. So what is my function value? So function value is what? Y minus x minus 2 multiplied by x square minus 2 multiplied by x multiplied by y, 2xy minus y square. Okay, this is my function, objective function. What is my direction? Descent direction? Descent direction will be what? This will be also a function of x and y, but this will have two values, no? This will have two values. So the first value will be what? First value will be what? 1 plus x. 1 plus x. And second value will be what? Second value will be what? Bracket 2y minus 3. 2y minus 3 divided by 2. Okay. So this is what my. So let me check whether everything is right or not. Here. Just respond whether you are able to hear me correctly or not, and you are able to see my screen. Okay. Fine. Then now I what I need to do? I have taken the initial guess and I have also taken this. I need to define some user defined epsilon value. Na? So suppose this epsilon I am defining E as 1e minus 8. Okay. And after each iteration, I want to store the values of what is the iteration of x and y. So that I am defining initially to zeros of suppose I need to go, I want to go till 10,000. First I should define the maximum iteration. I define iteration Suppose I want to go up to maximum 10,000 iteration. So this will be what? 10,000, not 10, maximum of iteration, comma 2. Okay. So this is defined now. Now I need to write the main part of the program. So Newton's method for 2D optimization. Na? 2D optimization. Okay, so for I equal to 1 to maximum iteration, we will go. Now what I will do, I will store the x first. In the first, I will store what? I will store x, and in the second column, I will store what? Y. Clear? Now what I will do, I need to find the descent. Before that, I need to define the h. Suppose we are initially we are doing for going for without satisfying the Armizo criteria. So I am just defining the h as h equal to 1. Okay, without Armizo criteria. So my descent will be what? Descent will be what? This will be what? Descent direction at x comma y. Okay. Now what is the formula? X at the k plus 1th iteration, that will be xk minus h multiplied by the descent. So now I need to define what? I need to define the error. So if the descent is very small, if the descent is very small, I will break. So for that I need to define the norm. So suppose I am defining b as a norm of descent. Now I'm doing if b is less than what? B is less than E. Means what? B is smaller than E. Then I will break. Otherwise, what I will do? I will define x equal to x minus h multiplied by descent first element, right? And y will be equal to y minus h multiplied by second value. Okay. So now I have done all the things that are required. Now suppose my loop has been ended. Now I need to define the minimum value. Minimum value that will be equal to what? That will be equal to objective function at the xy at last iteration. So this is my minimum value. Now I want to display. Suppose I want to display iterations that will be equal to what? I I want to display what? Now I want to display x and y. X. Similarly, I want to display y. I want to display minimum value. This will be equal to what? Now, if I say first, I need to save this. Suppose I am saving as week 11. Okay. Now I suppose I run it. So this is my minimum value. It is arriving at what? -1 and 1.5. Okay, but it is ran only 2 iteration. After 2 iteration only, it has been converged. Okay, after 2 iteration only, it has been converged. So whether it is correct or not, we can verify this by using the example that has been covered in the class. Okay, so I am commenting this now. Now this is x square plus 2y square minus 2xy minus 2x that has been covered in the lectures, and corresponding descent will lead to x minus 2 divided by 3, y minus 1 divided by 3. If I run for this case, it is running for a while now. Okay, it has converged after 46. No? There is one mistake I have made. Just 1 second. Okay. So yeah, it is converged. It has been converged after 46 iteration. X equal to 2, y equal to 1, and the minimum value is -2. So our code is correct. Na? We have verified with that. But in our case, it is converging after second iteration only. Okay. Now we need to do the plotting. That I will do in the next class. Okay. I will just add the contour plot, and on that, these points. Okay. So clear? So in this week, what we have seen? Optimization problem, which is nothing but a minimization problem. So first we have seen one-dimensional unconstrained optimization. How we can do this analytically, and if the analytical solution is not possible, we need to go for the numerical method. So first we have seen the random search method, where in the interval we assume some value randomly, and if we iterate for large number of iterations, we go for large number of iteration, we can reach to a solution. Okay. Then we have seen there that the optimization for the problem can be converted to a root finding problem. Similarly, a root finding problem can be solved using the optimization techniques. Then we have seen the region elimination method. There we have reduced the interval to get the desired solution. Here we have seen a method known as golden section search method. Then we have seen the Newton-Raphson method for 1D case, which is a class of gradient-based optimization problem. That is the default and standard method for optimization problem. Okay. Then we have seen the multi-dimensional unconstrained optimization problem, how the gradient and the Hessian are used to find out the minimum of a function. Then we have seen what is the physical significance of the gradient, that the gradient indicates the direction of the normal and function increases at the fastest rate when we go in the direction of the gradient, and it decreases at a fastest rate when we go in opposite direction to the gradient. Okay. So this method is known as gradient descent method. When we move opposite to the gradient to find the minimum value of the function. Okay. So then we formally defined what is gradient descent method. They are based on the value of dk and hk. Many methods can be possible in the family of gradient descent method. First method that we have seen, the steepest descent method. There we have assumed that the direction is opposite to the gradient direction, and this step size can be considered as a constant, or it can be calculated using the line search method. There we can do such that this phi k, that phi of h of k, that is the only function of hk, we can minimize it to find the hk. But again, this can be sometimes computationally extensive, so we do not go directly here, but we do the partial minimization, that is backtracking line search method. Here we satisfy the Armizo condition. What is Armizo condition? In the Armizo condition, this should be satisfy this equation, this inequality. So we assume h equal to 1, some small beta value between 0 to 1, and we check whether the Armizo condition is satisfied or not. If it is not satisfied, we replace h with tau of h, where tau belongs to 0 to 1. Typically, we take tau equal to 0.5, and then we again take, if Armizo condition is satisfied, we stop there. Otherwise, we do again replace h, current h with h divided by 2, or h multiplied by tau. Then we have seen how we can extend the Newton method from 1D to n-dimensional case, and also how we can apply the Armizo condition here to improve the convergence. We have also written down the program for this function using Newton's method, how we can do the minimization or the optimization. But this contour plot we haven't shown, we will show in the next class. Okay. We have solved some example problems also. So this is what we wanted to discuss in this week. Just 1 second. Stop. Clear. Now let me stop the sharing. Stop the recording.